no calculator problem, got Taylor Polynomial, Euler's method, and then just a differential equation integrating both sides here. So this could be a really good problem for us. I think we can be perfect with all parts of this thing, right? The first part says write a second degree Taylor polynomial about x equals 1 right there, and then use it to approximate something. So remember, just start with our main definition of a Taylor polynomial. We're about x equals 1, so that's our c value. So we're going to go f of 1, f prime of 1, x minus 1 to the first over 1 factorial, f double prime of 1, x minus 1 squared over 2 factorial. There's our second degree. So they started with that main definition, and then we were told f of 1 is equal to 4. So they told us that one. F prime of 1, we got to plug in x equals 1 into the derivative. So they give us the derivative, but when x is equal to 1, we know the y value is equal to 4. So I got to plug in x equals 1 and y equals 4 into this first derivative. And so that's what I did right here. I had 4 times 1 ln of 1. Ln of 1 was 0. So I had 0 times 4. F prime of 1 was equal to 0. So that whole term just disappeared. And then f double prime of 1, where do we get that one at? Oh, they flat out told us that f double prime of 1 was equal to 4. So I didn't have to do anything fancy on that one. So they told us that one was also 4. So then you just simplify that, and then boom, there's our second degree Taylor polynomial, and then use it to approximate alpha of 2. So that means we'll take the 2, plug it in for that x right there, no calculator. And so just be careful with your arithmetic there. Pretty good first part, basic definition of the Taylor polynomial, plug the stuff in, and then just use it for something. All right, Euler's method. Again, the challenge of this is make sure we can do this without the calculator. Starting at x equals 1, 2 equal steps to get to 2. So we're going to go 1, 1.5, and then 2. So our delta x is going to be the 0.5. So we'll use our main Euler's method according to our Euler's method video there. We'll set up our little table there, x, y, delta x times dy dx, and then we'll add up these two columns to equal our new y value right there. So we're starting with 1, 4. That was given to us. And then my delta x is equal to 0.5. So I'm going to go 0.5. And then the dy dx means I got to take the 1 and the 4, plug it into the first derivative. And that's what we did up here. I already took the 1 and the 4, plugged into the derivative, and I was able to get 0 for that. So it's just going to be 0.5 times 0. And then we're going to go 4 plus a 0 to get the 4. And then I put that right there. And now we're using this. 1.5 and 4 is the x and the y. And so I went to the side here. So that's why I put this little asterisk right here. I went to the side. So I had to go delta x times dy dx. So my delta x is 1/2. The dy dx means I got to take the 1.5 and the 4, plug those into the first derivative for the x and the y. So that's what my work is right here. I had 4 times 3/2 ln of 3/2. All right, and then that was just like 6 times 2 times 1/2 to get 3 ln of 3/2 right there. And then remember, you add up the 4 plus 3 ln of 3/2. That's what we get right here. And I don't have to keep going. It would be tough if I had to go another time and plug that stuff in it right there. It'd be get real messy. But you stop right there because you're at x equals 2, and then that's your y value right there. So get that 4 plus 3 ln of 3/2 right there. So I think I like that part A. I like that main definition of our Taylor polynomial, plugging stuff in. I like part B. I like doing that Euler's method there because they usually keep that stuff pretty darn doable without the calculator. So just make sure you practice that, and that's easy for us. And again, this problem, we could be 100% on this stuff here. All right, and then the last part for part C says find the particular solution to the differential equation. So they give us the derivative, and they're asking us to get the original function. So you know we're going to separate our variables if we need to, get the y's with the dy, x's with the dx, integrate both sides, plug in the initial condition for the point 1, 4, and then use that to figure out the c value, and then we'll have to solve that for the y. So you see all my work here for that. I started with this, multiply both sides by the dx, and remember, you're going to lock those differentials into place. You have to get the y's, do legal algebra, divide both sides by the y. Now I have the y's with the dy, x's with the dx. So this integral is just an easy ln of y. This integral here, you have a normal thing times a weirder thing. When you have the ln in that integral and it's not a u du, it's going to be integration by parts, and you're not allowed to use a shortcut there. You have to let the u be the ln part of that problem. That derivative doesn't go down to 0, so you can't use your tabular method on that. So let the u be the ln, do your du, the dv is the rest of the problem, do your integral, and then use your formula. You go u times v minus the integral of v du. So I did u times v minus the integral of v du. So I multiplied those together, the 1/2 popped out, x squared over x was an x, had an easy integral there, integrate that to get x squared over 2. So I just carried that stuff down. So I integrated both sides, had to do integration by parts there. So they like to do that for the BC stuff. Always put the plus C on the side the X's are on. And then I always stop right there, take the point that they gave me, the 1, 4, plug that in place for the X's and the Y's, and use that to figure out your C value. So that 1 was there, but the ln of 1 was 0. So that piece went away, and I moved that over. And I got the ln of my C value is that ln of 4 plus the 1/4. They're usually, when I plug it back in, I like to put that 1/4 first because it's not part of the ln. So I don't want there to be any sort of weirdness going on with any of the notation right there. But there's a C value. So all I do is plug that in right there. And then you're supposed to solve this for the Y. And a lot of times you'll see me move the ln's and stuff over on one side and stuff like that. But you practically already have the Y by itself already. So all you had to do is use your main definition of your log now. You're going to go E to all of that stuff is equal to Y. So just make sure you're careful with everything, carry everything down, put that stuff in parentheses, and then boom, we're done with this problem there. So nice Taylor one, nice Euler method, nice just do your integrals there. This is all of our strengths. There's nothing too crazy in there. It's all of our strengths. You guys know how to integrate the stuff. Just be careful with your integration by parts. And if you mess up anything, just convince yourselves that, hey, you can do every single part of this problem. That's some good stuff right there. The circus